Dear students, this is our sixth lecture on water chemistry, and we are discussing the processes for softening of water. Uh, in the previous lectures, we have discussed about lime soda process and geolite process. In this lecture, we will be discussing deionization process, and in addition, we will be discussing a topic desalination of salt water. So, as I have told you in the previous lectures also that the water which are to be used for industrial purpose, that should be free from any type of salts which cause hardness. And these salts, they are mainly calcium salts, magnesium salts, or iron salts. So otherwise, if these salts are present in the water which we are using for industrial purpose, then those salts, they will be responsible for scale and sludge formation in the boilers. Then these salts can also cause corrosion in the boilers, and that will be very damaging for our industrial equipment. So therefore, the industrial water which is to be used, that should be free from hardness producing salts like calcium, magnesium, or iron salt. And this process of removing hardness producing salts from water is known as softening process. And as I have told you that these are the methods which are used commonly for softening of water. And out of these, we have already discussed lime soda process and geolite or permutate process. This mixed bed deionization is almost similar to ion exchange or deionization or demineralization process. So we will be discussing in this lecture mainly this process, ion exchange or deionization or demineralization process. Now, deionization process is that hard water is made a soft water using ion exchange resins, and this process therefore is also known as ion exchange softening process. So here the all dissolved salts from water, they are removed, and hence this process is known as deionization process or demineralization process, because all dissolved salts or minerals, they are removed in this process. And the whole process of deionization, this require the passing of water through two types of ion exchange materials. And these two types of ion exchange materials, one is cationic exchange materials, and other is anionic exchange materials. So they will remove all the salt content present in the hard water. So when the hard water is passed through these two ion exchange processes, the all dissolved salts, they are removed from water and water becomes soft. And the process is known as deionization or demineralization process. Uh, then the word soft water, as you already know, means that it does not have these ions, calcium 2 plus ions or magnesium 2 plus ion, because these two ions, they are responsible for the hardness present in the water. And this hardness may be temporary hardness or permanent hardness. Temporary hardness is when these calcium and magnesium ions, they are present in the form of bicarbonates, and permanent hardness when these are present in the form of chlorides or sulfates. So if we remove these ions, calcium or magnesium ions, then this water will be called as soft water. and it may contain some other ions like sodium or chloride ions or potassium ions, but it should not have this calcium and magnesium ions. The demineralized water does not have any ion, including hardness producing ions. So every soft water, that means is not a demineralized water, whereas every demineralized water is a soft water. So this should be clear to us that this line is there for deionization process. Then chemical production, pharmaceuticals, electroplating, television tube production, and leather good processing. These are the applications for deionized water, because the all these processes, they required demineralized water. Then theory of ion exchange resins is that these ion exchange resins, they are insoluble cross-linked long chain organic polymers, which is having a microporous structure. And on these organic polymer, there are functional groups which are attached to the chains, and these functional groups, they are responsible for the ion exchanging properties of these ion exchange resins. So if the resin contains carboxylic acid or sulfonic acid as the functional group, then those ion exchange resins, they will replace H ions with the cations. So that means if we are having calcium and magnesium ions in the hard water, those calcium and magnesium ions in the hard water, they will be replaced by H ions, and the calcium and magnesium ions, they will get attached to the carboxylic acid group or sulfonic acid group present on the ion exchange resin. So the calcium and magnesium ions, they will be shifted to the ion exchange resin, and H ions from ion exchange resins, they will be replaced to the water. Similarly, if the resin contains amino group or substituted amino group, then this functional group is present. This is a basic functional group, whereas this was an acidic functional group, and this will replace anions with anions. Anions with anion means this anion present on the resin, that will be replaced with the anion present in the hard. Then, as I've told you, that these ion exchange resins, they are of two types: cation exchange resins and anion exchange resins. The cation exchange resins, they are mainly styrene-divinyl benzene copolymers, and on these polymers, the functional group present, as I have told you, is a sulfonic acid or carboxylic acid. So when these copolymers, they are sulfonated or carboxylated, they will get their functional groups on the polymer, and these functional groups, they will exchange hydrogen ions with cations in water. And the most common cation exchange resins, they are amberlite IR 120 or DOX 50 or nalcite HCr. All these are trade names for different types of cation exchange resins, and the basic polymer which is present in all these three types of cation exchange resins is styrene divinyl benzene copolymer. And in some cation exchange resins, you will have sulfonic acid as the functional group. In others, you will find that there is carboxylic acid as the functional group. So this is the only difference. Otherwise, this is a trade name for these cation exchange resins. So we can represent cation exchange resins like this: R, H positive. R is the resin, and H positive is the ion which can be replaced by the cations of the hard water. So basically, the reaction which takes place is this. This is cation exchange resin. R is resin, and this will substitute these H positive ions by the calcium 2 plus ions present in the hard water. So our resin will become having calcium ions, whereas the H ions, they will be released into the hard water. Similarly, if our hard water contains magnesium ions, those magnesium ions, they will be substituted into the cation exchange reason by replacing H ions. So these H ions, they will go to water, and these will become attached to the polymer, which is ion exchange resin. Then second category of exchange resins is anion exchange resins. So they are again styrene-divinyl benzene copolymer or amine formaldehyde copolymer. So on both these copolymers, we can introduce those functional groups which are required uh, for our reaction. So these contain amino or quaternary ammonium salts as functional group for exchange with the hard water. And in addition, we can have quaternary phosphine also, and tertiary sulfonium groups also present on the anion exchange resins as an integral part of the resin medium. Then when these are treated with dilute sodium hydroxide solution, the above groups, they are able to exchange their OH ions with the anion in water. And most common examples of anion exchange resins, they are amberlite 400, DOX3 and Geolite F. These are the trade names for different types of anion exchange resins, and these resins can have either this or this or this or this functional group present on the anion exchange resin, which can exchange OH negative ions with the negative ions present in the hard water. So we can represent these resins as ROH negative, and R is our resin, and these are the functional group present on the resin. And these functional groups, they can be exchanged with either sulfate ions, chloride ions, or carbonate ions, which are present in the hard water. So these are the three reactions which will take place. uh, Resin will react with the chloride ions. These chloride ions will get attached to resin, and these will be sent to the water. Then OH negative will send to water, and sulfate ions will get attached to resin. Similarly, carbonate ions will get attached to resin, and OH ions, they will be exchanged in the water. So this is the process how this reaction take place. The hard water is first passed through cation exchange. So there are two columns. First is cation exchanger, and second is anion exchanger. So in the cation exchanger, we know that H positive ions, they will be exchanged with calcium and magnesium ions. So because cation exchange reason will be either sulfonic acid or carboxylic acid. So these H positive ions, they will be freed, and they will enter the water. Whereas these calcium and magnesium ions, they will get attached to sulfonate group of the polymer, and they will become attached to the resin. So that is how H ions, they are exchanged with the cations present in the hard water. Then after this, that water where exchange of cations has taken place will pass through an ion exchange region. And in an ion exchange region, we know that OH negative ions, they will be exchanged with sulfate ions or chloride ions or carbonate ions. So that is how the hardness in terms of cations of the metal of calcium and magnesium and their anions, they are removed from the hard water, and hard water will become the soft water. The H ions and OH ion, which are free from cation exchange resin and anion exchange resins present in that column, they will get combined to produce water molecule. And therefore this water coming from an ion exchange column become free from cations as well as from anions, and this ion free water is known as deionized water or demineralized water. So this is how the whole process of deionization or demineralization takes place. Then after the process has taken place, we can regenerate the ion exchange resins. The ion exchange capability of these resins toward exchange ions from water is based on their ion exchange potential. So when the process has completed, that means the capability of these ion exchange resins that has either been lost or it has decreased to some extent, depending upon that how many of H ions or OH ions have been replaced by the cations or anions of the hard water. Then these exhausted cation exchange resins, they can be regenerated by passing through dilute HCl or dilute sulfuric acid. So we know that these calcium ions, they will be substituted by H ions present in the HCl or H2SO4. If we react with HCl, H ion will go to the resin and calcium ion will react with chloride, and we will get calcium chloride, and resin cation exchange resin will be regenerated. And then once it has been regenerated, that can be again used in the cation exchange reaction. Then after this reaction has taken place, then column is washed with deionized water, and the washing that contains these calcium ions or magnesium ions or sulfate ions from sulfuric acid or HCl, chloride ions from HCl. So then the process of regeneration is completed. Similarly, exhausted anion exchange is a column that can also be regenerated if we treat this with dilute sodium hydroxide. And we know that sodium hydroxide, hydroxyl ion present, they will be exchanged with the resin, and the sodium sulfate will be removed. So this sodium sulfate, sodium ions and sulfate ions and uh, or chloride ion, if we use other material, they are again passed on to the same. So this is how the process of regeneration of exhausted cation exchange resins or exhausted anion exchange resins that can be done. So this is the process how this is cation exchange resin column, and this is anion exchange resin column. What we do is first we pass hard water from this inlet, and this passes through cation exchange resin in the first column, and we know that here calcium and magnesium ions they will be removed, and H ions they will be sent to the water. And at this point we can say that deionization or demineralization process is half complete. So when positive metallic ions they have been removed in this column, and the water now contains positive hydrogen ions which have been replaced by calcium or magnesium ions. Then this water containing H positive ions in place of calcium or magnesium ion passes through this anion exchange region, and in the anion exchange region the negative ions present in the hard water, they are also exchanged with hydroxyl ions. Hydroxyl ions are released. Those H ions and hydroxyl ions, they combine to give us water, and rest of the hard water salts, anions over here, cations over here, they are removed and the process is completed. So you have seen that ion exchange water softening process can remove nearly all calcium and magnesium ions and all other anions which are present in the hard water. And after the softening, the hard water contains only 5 to 10 ppm of iron and magnesium only. All other calcium, magnesium and other anions, they are removed from the hard water. So in that way this ion exchange reaction process is very effective. The advantages, as I have told you, this is very efficient process, highly efficient process. More than 99.9% of all ions they are removed, and that is why we say that this is a deionization or demineralization process. Recovery of water is very high, 97% of the water is recovered. Then selective impurities can be removed very effectively, and process can be used to soften high acidic or alkaline waters, because acidic or alkaline cations and anions, they can also be removed through this process of ion exchange. And this produces water of very low hardness, say from 2 to 10 ppm. And this is very good for treating water for use in high pressure boilers. So this water produced will not have any sodium hydroxide or carbon dioxide which we have seen in the zeolite process. So those are also removed, and that is why this is a big advantage of this process. But disadvantage is that equipment is very costly, and these ion exchange reagents, they are very expensive chemicals. So this is the disadvantage, that economically the process is very expensive. Then if water contains turbidity, then output of the process is reduced. The turbidity must be below 10 ppm, only then this process is effective. And if turbidity is more before this process, we need to remove by any other process, either through adulation or to filtration. Then another disadvantage is that this process is not effective for removal of bacteria, H2S, silt or sand, lead nitrate, pesticides, and many other types of organic and inorganic compounds. So these category of pollutants or hardness causing materials, they are not removed by this process. This is a big advantage of this, big disadvantage of this process. Then next is desalination of water. We have seen that of the total water on earth, 97% of the water is contributed by oceans. That means seawater is 97%, and this seawater contains about 5% salts. And because of the presence of this salt, the taste of this water becomes peculiar, that is brackish taste or salty taste. And that is why this water is also known as brackish water. So in order to make this drinkable, we need to remove this brackishness or salination present in the water. The process of removing this common salt, that is sodium chloride, from brackish water is known as desalination. And this is very important process, and this can take place either by electrodialysis, reverse osmosis, or distillation. The electrodialysis is a process by which oppositely charged ions, they are pulled out of the salt water by passing direct current using electrodes and ion selective natural or synthetic membranes. So advantage of this electrodialysis is that cost of the plant installation is very less. So here what happens is that when current is passed through electrodes, that means this is cathode, this is anode at the other end of the water. Anode we know is positively charged and this is negatively charged. That means this will attract cations, this will attract anions towards itself. So sea water is present in the center, and this towards this end we are having ion selective membranes towards both the ends, and this is one is anion selective membrane, other is cation selective membrane. The cation selective membrane is permeable only to cations. So because through this membrane sodium ions they are to be removed, that means this is a cation selective membrane, and cation selective membrane will allow only cations to pass through. So sodium ions they can pass through this membrane and go to this side, and similarly this is anion selective membrane. So this will allow only anions to pass through it and not cations will not be allowed. So chloride ions they will pass through this end. So this is how on application of current, sodium ions from the salt will go to this side, chloride ions will go to this side, and we will here we can collect our brine, that is sodium chloride, and this is how the seawater can be removed. From the seawater we can remove sodium ions and chloride ions. So from this end we can have our pure water, because all the sodium and chloride ions they will shift to anode and cathode respectively. And this process of removal of sodium chloride through uh, application of current using electrodes and these cation selective and anion selective membranes is known as electrodialysis. The next is reverse osmosis. We know when a semi-permeable membrane separates two solutions of different concentration, the flow of solvent takes place from dilute solution to concentrated solution, and this process is known as osmosis. But however, if opposite happen, that is if flow of solvent take place from a solution of higher concentration to lower concentration, then that process is called as reverse osmosis. So the flow of solvent takes place from concentrated solution to a dilute solution, that is called as reverse osmosis. So that reverse osmosis process is applied to purify water by removal of sodium chloride from this. So when we are having brackish water, the concentration of sodium chloride is higher in that water. So if we pass it through a equipment which is used for reverse osmosis, then sodium chloride can be easily removed, and seawater which is having higher concentration of sodium chloride will become pure water where concentration of sodium chloride become low, and when this is done through semi-permeable membrane. And most commonly used semi-permeable membranes that consist of cellulose acetate or PMMA, polymethyl methacrylate, or polyamides. These types of polymers, they membranes made from these types of polymers, they are most commonly used in reverse osmosis process. So this is the process. So here this is the high concentration water containing sodium chloride, and this is the semi-permeable membrane. So this will not allow sodium chloride particles to pass through this semi-permeable membrane. So sodium chloride which is in higher concentration, when pressure is applied, that is sodium chloride is removed through this semi-permeable membrane to outside, and we get pure water through this process. And this process of application of pressure, where a high concentration water having sodium chloride is transformed into low concentration pure water, is called as reverse osmosis. Then distillation is a simple distillation process which we do in chemistry. That this is simply heating the salt water. Then these dissolved salts, they will remain in purified form below, and then in the form of vapors, the water will be evaporated, and that will be captured in the gaseous state. And distillation is a very high efficiency process, and this can be piped for distribution system. This is the book which has been used for this lecture, Chemistry for Engineers by Harish Chopra and Anupama Parmar. The book has been published by Alpha Science UK, and at the national level this has been published by Narosa Publishers, Delhi. Thank you very much for your patient hearing, and this completes our series of lectures on water chemistry. Thank you very much.